All right, today we're diving into something that sounds like it's straight out of a sci-fi movie, but it's actually grounded in some incredibly clever physics. We're talking about thermal cloaks.
I mean, just think about that for a second. Not invisible to light, but invisible to temperature itself. You could literally put something in a furnace, and the inside would stay completely cool, totally oblivious to the fire raging just outside.
So where did this wild idea even come from? Well, it was actually inspired by all that research into light-bending invisibility cloaks. Scientists started wondering, hey, if we can bend light, could we do the same thing with heat? The answer, it turns out, was a big yes. And just like that, a whole new field was born, transformation thermotics. You can think of it as the science of creating a GPS for heat, telling it exactly where to go.
Okay, so how on earth do you convince heat, which naturally wants to spread out everywhere, to follow a specific path? Well, the secret is all in the materials.
The key ingredient here is something called a thermal metamaterial. Now, this isn't stuff you can just dig out of the ground. These are designer materials engineered from the ground up to have thermal properties that are, frankly, impossible in the natural world. They give us this incredible, fine-tuned control over one of the most basic forces in the universe.
Okay, here comes the big sciencey term for how this all works: anisotropic thermal conductivity. But don't let the name scare you off. The core concept is actually beautifully simple, and the best way to explain it is with a good old-fashioned piece of wood.
So you know how wood has a grain, right? It's way easier to split it along the grain than against it. Well, heat is kind of the same way. In a normal material, it just flows in a straight line from hot to cold. But with these metamaterials, we can create a sort of thermal grain. And heat, being a little lazy, will always take the easiest path. So by carefully designing the curve of this grain, we can literally make heat flow smoothly around a central region, leaving whatever is inside totally protected.
So the theory is fantastic. It all makes sense. But there was a huge roadblock stopping this from being really useful in the real world.
For years, scientists had the math all figured out for simple things, like circles or spheres. But let's be honest, our most advanced tech isn't built out of simple circles. It's full of all these intricate, complex parts. And trying to create a thermal cloak for those shapes, that was a massive mathematical headache.
So researchers decided to focus on two really important shapes: hexagons and dodecahedrons. And they didn't just pick these randomly. Hexagons are everywhere in advanced structures because they're strong but lightweight. And dodecahedrons, they're key for packing things together in 3D as densely as possible. If you can't protect these fundamental building blocks from heat, you basically hit a dead end in material science.
And this is where the paper we're looking at today comes into the picture. A team of researchers decided they were going to crack this complex shape problem once and for all. And what they came up with was basically a universal key.
These researchers from Xianjiatong University came up with this incredibly elegant new mathematical method. Think of it less as solving one specific puzzle and more like creating a blueprint or a universal recipe that could calculate the exact thermal grain you need for all sorts of super complex shapes.
And get this, it wasn't just a one-off solution for a hexagon. As they say right in their paper, this method works for pretty much any 2D or 3D shape that has some kind of symmetry. That's what's so powerful here. They didn't just solve one problem, they created a tool that can solve countless others.
Of course, having a cool blueprint on paper is one thing. You've got to prove it actually works. So the researchers fired up some powerful computer simulations to see if their designs would hold up under pressure.
First up to bat was the two-dimensional hexagon. They basically set up a virtual test for the hot side and a cold side to see what the heat would do.
And wow, just look at these results. On the left, without the cloak, you see the heat flowing straight through, no problem. But on the right, with the cloak active, look at that. The heat is bent perfectly around the center. It's like the central region doesn't even exist. It's completely isolated.
This chart just makes it crystal clear. The temperature gradient, that's just the change in temperature inside, is that blue bar. Without the cloak, it's high. With the cloak, look at that second bar. It's at 0, zilch, nada, a perfect score. The object was literally invisible to the flow of heat.
Okay, 2D is impressive for sure, but we live in a 3D world, right? So now for the main event, proving this could work in 3 dimensions with that super complex dodecahedron.
So in the 3D test, without the cloak, the lines of equal temperature just pass right through in these neat little rows. But once the cloak is turned on, you see this absolutely beautiful, fluid-like motion. The heat is forced to bend and flow around that protected zone, just like water in a stream flowing around a big rock.
And the final result inside that protected zone? You guessed it. Just like in the 2D test, the temperature gradient was a perfect 0. They did it. They created a working 3D thermal cloak for a seriously complex shape.
Now this is way more than just a cool physics experiment. This mathematical blueprint has some really profound implications for real-world tech.
So, why does all this matter? I mean, the possibilities are huge. Think about protecting delicate computer chips, letting them run way faster without melting, or creating perfectly stable temperature zones for super-sensitive scientific experiments. You could even stop critical parts in a jet engine or a spacecraft from warping under extreme heat. And yeah, of course, there's the whole making things invisible to thermal cameras thing.
But here's the real takeaway. This research finally bridges the gap between a fascinating idea and a practical tool for engineers. It gives us a way to protect the actual, complex components that our entire modern world is built on.
It really makes you wonder, doesn't it? We started with bending light, now we have a blueprint for bending heat around almost any shape you can imagine. What's next? Bending sound? Magnetic fields? It feels like the age of metamaterials is really just getting started, and this whole frontier of controlling these invisible forces is wide open for discovery.